Hello, everyone. Welcome to another DaSSWeb. Today, I have the honor and pleasure to introduce Daniel Peña. I and Paula Brito would like to thank Daniel for accepting to talk to us today. Daniel is very well known worldwide. It almost does not need introduction, but never. Daniel is an emeritus professor at the Department of Statistics, University of Carlos III, Madrid, and member of the Royal Academy of Science of Spain. He was full professor at Universities Polytechnica and has been visiting full professor at the Universities of Wisconsin-Madison, British Columbia, Toronto, and the University of Chicago. He was the founding director of the Department of Economics, the Department of Statistics, the Institute of UC3MBS in Financial Big Data, and President Rector of the University Carlos III de Madrid. He has an extensive list of publications, books, and research articles on time series, robust and diagnostics methods, multivariate analysis, Bayesian statistics, and econometrics, with applications of social sciences, economics, and engineering. He has supervised more than 30 PhD theses, has been invited speaker more than 80 times in the most important statistical meetings, including several times at joint statistical meeting of ASA, EMA, and RSS, and has given seminars and short courses in more than 100 universities. He has been director da Revista Estatística Espanhola and associate editor of the Journal of Business and Economic Statistics, Statistica Cínica, International Journal of Forecasting and Statistical Modeling. His research has received several awards, such as the 2006 Uden Prize for Best Paper in Technometrics, 2011 Time First Prize in Economics, and the 2011 Award Engineer of the Year by the Colégio Oficial de Engenheiros Industriais, Madrid. He is a fellow of the American Statistical Association, the Institute of Mathematical Statistics, the Royal Statistical Society, and elected member of the International Statistical Institute and member of the Royal Academy of Sciences in Spain. His publications have received more than 12,000 sites in Google Scholar. Thank you for accepting to talk to us, Daniel, and the floor is yours.
Well, thank you very much. Thank you very much, Maria Eduarda, for inviting me and for your very kind presentation. Well, the talk I am going to present is a joint work with RSA from the University of Chicago, and the title of the talk is Selecting the Number of Clusters in Time Series, and it's not moving. Okay, this way. Okay, and well, the presentation is going to be organized as follows. There will be a brief introduction in which I will try to convince you that clustering in general is important, and the clustering in time series is very important as well, of course, and that we need new ways and better procedures for clustering time series. Then I will talk about a proposal that that we have devised to find the number of groups, or the number of clusters in time series. And then I'll present some Monte Carlo studies and an application. And finally, there will be some brief conclusions. Well, as all of you know, the data that we have in hand to be analyzed and the computation facilities that you can use to analyze data has driven statistics along the history, I think. And now we are for the first time, let's say, in the last 25 years, so in this century mostly, more and more sets of time series, of high-dimensional time series are being recorded with electronic device in an automatic way. And so we have very large set of time series. This large set of time series, as it happened with independent data as well, are usually heterogeneous, and among the many sources of variability that we can find in this type of data are, of course, outliers, very, very often clusters. Clusters means that the different part of the data have been generated by a different procedure. It could be a model that we can more or less imagine, or it could be just a different way to do things because the condition in which the data has been taken is different. And so we need new methods for forecasting high-dimensional time series with cluster and outliers, and I am going to talk mostly with clusters in today's talk. Well, clusters is important in general, although it was a neglected part of statistics for many, many years. Actually, some of the first clustering procedures were almost developed a little bit outside the statistics, because the paradigm of statistics at the end of last century was the data has been generated by a model. And so cluster that is like assuming that we have different models for different parts of data, or different process generating different ways of generating the data, was not considered a part of statistics, but slowly was being introduced. And I found, and I was convinced that clusters were important at the beginning of my career. I was studying with an economist, a friend of mine, and at that time, I am talking about the 80s in Spain, and at that time, there was a law that controlled the rent of the apartments all over Spain. And the government was deciding whether or not this was a law that was covering their objective of helping, let's say, people that have difficulties and that have low income, or maybe women with children that were by themselves and so on. And so they decided to take a very large sample of data and try to see who were the people that are having the largest benefit from this law. So the way to measure this was very simple. So you compare the cost of the apartment with the cost that is expected to be for this apartment in a free market, because there was some sort of free market in Spain at that time as well. Most of the apartments were under rare control, but there was some part that were in the free market. So we have data for both cases, and then you can relate the benefits that people obtain, the people living in the apartment, with some characteristics as their age, their gender, or other things, and then have a better idea of the benefits of the law. And then we found, we were studying data from some area of Madrid, and then we found that there was, of course, we have a regression with many variables. At that time, it was a very large sample for the time being. I don't know, we have several thousand of data. That was very large at that time. And then we found in this area a negative relationship between the size of the apartment and the price. The price. That means if you think that apartments that were larger, the price, the average price, was smaller than for the smallest apartment. Of course, it doesn't make sense. This situation was unbelievable from the economic point of view, that the elasticity to price was negative in this area. And so we decided to look at the data more carefully. And then we make a lot of plot and analysis, but in summary, to make a long story short, what we found is what you see in the picture. In one area of Madrid that was the area of Cuatro Caminos, just in case that some of you maybe know a little bit of Madrid, that was close to the center, but a little bit outside the center. There were the apartments that were built in the 19th century mostly, were houses not very large, but large because families were very large, and usually they have 4 or 5 rooms, but they were in very bad shape, and the price of this, some in a very bad condition, not well preserved, and so on. And the price of these houses was not very large. So actually, in that part of the, I don't know, you see the mouse, but well, you see in the down part of the figure, you see that there is a group of data that follow a straight line, more or less, whereas and this corresponds mostly to the larger, you see size is in the x of coordinates over here, and so you see that there are a group, and then there is another group of smaller house apartment that were built at that time, that were what the people were doing was demolishing the old apartment, building new apartments that were smaller in size, but much more fancier, and of course, much more expensive. And so the relationship, as you see in the picture, between the size of the apartment and the price for the whole data is negative, but of course, inside each group, it was positive. Well, that when you put together things that are different, you can get any result is a null and is well known, a null paradox in statistics. But we have forgotten in the analysis of data quite often that this situation is going to happen when we have large data set. And now that the data is larger and larger, and in a more automatic way recorded, and in a more heterogeneous situation, this kind of problem that means having clusters is going to happen more often. And as you see, if we are not aware of this possibility and we didn't try to find the clusters, then we cannot make a good understanding of the structure of the data, and it's very difficult to get good forecasts from this sort of data. Well, now thinking in time series, several procedures have been developed for clustering time series. Roughly can be classified in non-parametric methods, and we have hierarchical. Well, the main idea is very simple. What you do is each time series is represented by a vector of features. Features could be, we will go back to this problem in a moment, could be correlation coefficient, or could be prediction, or would be whatever you are interested in. But each time series is represented by the vector, and then you have a set of vectors, and you want to make clusters with this point in the space. And then several procedures can be used. Some non-parametrics, of course, you can always assume that you have a mixture of distribution and use a model-based approach that is like fitting a mixture of distribution. And there are some kind of semi-parametric approach, and what is considered deep learning cluster is belongs to this, let's say, some kind of semi-parametric approach. But I am mostly interested in the situation in which we don't want to assume any model, and so we want to use a non-parametric approach, and there are 3 ways to do so, mostly. The first one is hierarchical clusterings. The main idea is you define distance or similarity between the vectors, between the time series, between the features that you have used to summarize the time series, and then you make group with these features, and you do a hierarchical classification. That means you start joining, I will explain this in a moment, you start joining the data and so on until the end. You can use partition methods in which you assume, well, let's assume that we have 2 groups. What is the best way to divide all this data into 2 groups so that the internal homogeneity of the group is the largest as possible? And then there are algorithms as k-means that in order to do so. And then you say, well, now with 2 groups, now I assume 3 groups or 4 or 5, and then you obtain the best solution for each number of groups, and then you decide with a criteria that could be a kind of information criteria, because of course the fitting increases when you increase the number of groups. So you have to penalize for the number of parameters and so on, and you can make a decision. And you have also used some kind of non-parametric density estimation, using some kind of mode estimation, trying to find in a non-parametric way how many distributions you have. Well, except with hierarchical clustering, usually what you do is to assume 2, 3, 4, 5 groups and so on, and then choose the resolution. In hierarchical clustering, you don't assume anything. Yes, you do some kind of classification, some information of the data, and then you decide how many groups you have. And that's the approach that we are going to use. So to use the information of a hierarchical clustering in order to decide about the number of groups. Another problem is that most of the procedures for clustering, of course, you can check whether or not there are more distribution, but they usually assume that there are groups or clusters, and there are not a simple way to start from the very beginning, whether or not you need to start the process of building clustering. And that's another problem that we will be dealing with in this talk. So, features in time series. What are the relevant, so how to summarize the information of the time series? There are two types of situation, depending on the objective that you have in mind. You have the first, and the case that has been more studied, but I don't believe that is the most interesting, but is the one that has been studied more, is the case in which you have independent series, and then you want to cluster the series according to their common properties, let's say. The second situation that I will going to talk about very briefly, the procedure we are going to present apply it in both cases, but it is simplest to explain with the first situation, and so we'll try to concentrate on the main idea in the simplest case. In the second situation, we are interested, we have a lot of time series, and the series have cross dependence, so they are not independent, they have a joint dependency, and you want to make groups taking into account the joint dependencies. So series that are correlated, cross-correlated, strongly cross-correlated will be in one group, and so you try to make group of in such a way that the groups are as independent as possible. But inside the group, you have a lot of dependency. Well, let's consider the first situation in which you have independent data and you can cluster them by univariate properties. Then there are several ways to summarize the time series. You can use the coefficient of the autoregressive representation of the time series. You can use autocorrelation coefficient, called simple autocorrelation coefficient, but you can use partial autocorrelation coefficient or inverse autocorrelation coefficient or any other measure that you are interested in. Of course, you can use information of the spectral domain as periodogram, ordinates. You can use forecasting. You can use also structural features as trends, seasonality, asymmetry, kurtosis of the time series, and create a vector of properties of the time series and do the clusters with them. And of course, you can use some nonlinear features of this. And as I said, usually when you have a large set of time series, you have dependency among them, and there are some ways to cluster the series by dependency, but I think I am going to skip that part because it's not crucial for the rest. There are some details, and so I am going just to concentrate, because I don't want to talk much more than 45 minutes. That is the limit, and if not, I am afraid that it will take maybe more time. And so let's think in the case of that we have independent time series. Okay, everything that I am going to explain can be generalized to the other situation. If you are interested, we can discuss a little bit, but later on in the discussion. But the ideas are similar. So the important are the ideas, and the ideas are similar in both cases. Well, suppose that we have made a hierarchical clustering of independent data. For instance, what you have in the plot here is the dendrogram, a hierarchical clustering made with 3 groups of independent autoregressive time series. So we have a total of 100 time series, not too many, but a number that is good enough to be represented and that we can see the picture. And we have a group, so this is simulated data, a group with 30 series, that is a second order autoregressive. So the second group that includes 40 series and it's white noise. And the third group with 30 series is a second order autoregressive, but with the first coefficient equal to 0. And it's different from the second order autoregressive, the first one, the other group in which we have a strong first autocorrelation coefficient of 0.7. Well, this is a hierarchical clustering. How a hierarchical clustering is made? Well, probably most of you know, because the idea is very simple, but just in case that some of you are not very familiar with hierarchical clustering, as it is very easy to explain, I will explain it briefly. What you do is you select a measure of distance. Well, first you select the vector of features of the time series. Suppose for the time being, to simplify, that you use is what it has been used here, I think, autocorrelation. For instance, you consider a vector of 3 or 4 or 5, it doesn't matter, for, let's say, autocorrelation of the time series. So its time series now is represented by a vector with 4 numbers that are the first 4 autocorrelation coefficients. Second, you define a distance between the series. Suppose that you use the Euclidean distance between the autocorrelation coefficient, to be simple. Then we build a matrix. We have a 100 time series. We can build a matrix of 100 times 100, in which we have in the diagonal 0, the distances, and then out of the diagonal, we have the distance between the two series that are represented by in the cell. So the 1, 2, 1, 3, and so on. So we are computing all the distances among the series, and we put in a matrix. Okay. Now, hierarchical clustering works in a very simple way. They look at the matrix and they say, which are the elements that are the closest, that have the minimum distance, and they put these two elements together. And now, these two elements together then are disappear of the matrix, because they are going to be substituted by the group of 2 members. And then we have to decide the way, what we need to compute the distance of a group of 2 members to the rest of the group. And we can, for this, we can take the minimum distance, the maximum distance, or the average distance, let's say. That is, you have 2 elements here, A and B. In order to find the distance to C, we can look at the distance between A and C, B and C, and then decide, are we going to take the largest one, the maximum value, the minimum value, or the average? Suppose that we decide to take the maximum value. That is probably the one that is used more often. Then that's what we do. So we have now a matrix in which we have 99, 99. And we do the same over this matrix that we have done before, and we keep going this and this and this until the end. For instance, suppose that we say, well, can you see the mouse if I move the mouse on the screen? Maria Eduarda, or you don't know? You see the screen?
Yes, we see the
mouse.
mouse.
Perfect.
Yes.
Perfect. Perfect. Suppose that you say, well, I don't know which is the smallest one, but it doesn't matter. Suppose that these 2 are the smallest one, okay? So then they form a group. Now I have to compute the distance of these 2 to all the others, and so on. And then you know how they are growing. So maybe these 2 are put together, then these 2, 2, 2, 2, and so on. When the process continues, it'll start putting groups larger and larger and larger until the end. Okay, that's the information. And then a dendrogram, that is what represented here, the output of a hierarchical clustering, simply put the heights that are here, the heights in which the links has been established. For instance, the 2 last group that has been merged are that group and that group, and they are merged at this distance. So you have the heights all the time. Well, that we propose, the height has been used sometimes in order to make clusters. And so some people say, well, actually, from an intuitive point of view, well, we may cut the heights maybe by here, and then we will have 2 groups, or we can cut by here, and then we will have 3 groups, or maybe we can go down by here, and we have more groups, 1, 2, 3, 4, 5, 6, and so on. I'm sorry. Oops. I'm sorry. But there is not a clear way to do so. And so several procedures have been proposed. I will review this later. But we think that more important than the heights are the jumps. What are the jumps? The problem is that the jumps are the difference in heights. So, the heights start, the output of the program is a sequence of heights that are increasing, of course. But we can look at the derivative of this function of the jumps that are this part. For instance, this group has been merged with this group. But what has been the height? The previous height was this one. The last one goes until there. So the last jump is this one. So we have another jump here. You have another jump here. We have another jump here. This is the largest jump that we can find in the data. And there are some other jumps, but we don't see the jump immediately because they are not so clear as the heights, and they appear in different parts. So we have to be very careful. So from an intuitive point of view, the jump, I suppose that this reason never, as far as we know, has been considered. We think that the important information are in the jumps, not in the heights. And that's what is written here. So first, what I have said is explained. The procedure to make a hierarchical cluster is what you have in the first part. And well, everything else has been explained. And now we go to the jumps, the difference in the heights. And so the idea that we are going to use is very, very simple. So we have a sequence of jumps. And now we have to think, what would be a reference distribution for the jumps in the case in which all the series have been generated by the same model? We have a homogeneous group. Okay, well, that's what I'm going to explain. But suppose we find a way to do so, then the procedure to find the group is very simple. What we have to do is we look at the quantiles, a large quantile of the observed jump that we have. Okay, you take a large quantile. Which one? Well, the best decision is not very clear because it depends how many groups you have and so on, and you don't know anything about it. But clearly, one of the largest quantiles. Okay, you have to choose. I will be more precise about this point in a moment. But so we choose a large quantile, and then we generate a reference distribution for this quantile using Bootstrap by simulation. How? Well, in the case of independent time series, it's very simple. All the series must be generated by the same model. So we can take any series at random. We will improve this in a moment, but for the main idea, that's good enough. We can take a series at random, see what model it follows, and then generate a set similar to the one that we have, but in which all the series follow the same model, and then apply the clustering and create then a sequence of jumps. Do it many times, and we can create the whole distribution. If we do 500 times, we have a distribution of jumps. And then we can compare the jumps that we have observed with this generating distribution that we have, and decide first if there are clusters, and second, if there are clusters, how many. One thing that we don't like of all the clusters, all the ways to find cluster, to select the number of clusters, is that the criteria that are around, all of us that we know, are not coherent. What does it mean? It does mean that if we suppose that we use any, for instance, the silhouette or the gap statistic, any criteria that you are familiar with, and then we decide that there are 4 groups, then we take each group and we apply the same criteria and we split the group again. And that's very uncomfortable because we don't know how to stop. So we want to have a criteria that is coherent. That means that if we say that this group is homogeneous, and I give this data to you, and you start applying the same procedure that we have been using to see if it is homogeneous, it must be homogeneous. It must be coherent. And so the only way to do it coherent, of course, it takes more work, but then is, so if the data is not homogeneous, we split into two, of course, using the largest height, the largest group. And then we start over. We take each group, and then we create a reference distribution for these two groups and see if we need to split, and we keep splitting until the end. Okay, that's the main idea, and that is what I'm going to explain. But you see, the idea is very simple. So the idea here, we have a little bit, I have tried to avoid mathematics as much as possible in order to give you the idea in the short period that we have. So we start with the observed jumps, and then the test, the number of jumps. If we have n time series, we have n-1 distances and n-2 jumps. Okay, and then we take a quantile, an upper quantile, and compare with the reference distribution. So the problem is to generate the reference distribution. More about this immediately. And if the test statistic rejects the null hypothesis of a single cluster, we split and apply to new group the same test and keep doing the same until more groups cannot be found. Now, how to select, how to generate the reference distribution? Well, for independent time series, forget about dependent time series. I am not going to say anything about dependent time series. For clustering independent time series, we need to select series from the group. We could take one at random and it will work, but a little bit better, because then we have always the same solution, is take a series that is representative of, let's say, that is more or less in the middle of the group. And one way to define this is what we call the median empirical quantile. The median empirical quantile is the series that is in the middle, according to L1 distance, the one that is closer to being in the center along the whole period. Because, I mean, being in the center in any particular moment is very easy. The problem is that there are no series that is in the center all the time, because the series cross over there. But the one that is closest to this, with that minimize the L1 distance, is the median series, the median empirical quantile. Well, we select this one, and then that's the one. Then then what we do, once the series have been selected, we fit in autoregressive models, and then we build bootstrap data matrices that are similar to the data that we have, but we are going to generate many other set of time series. We use the same model, the model that we have used for the series that has been taken as representative of the real data that we have, and use this data to generate a sample similar to the one that we have. So if we have n time series, you generate another set of n time series. For clustering by dependency, nothing. And then we apply the simulated, we apply these bootstrap samples, and using these bootstrap samples, we generate a distribution of the jumps, okay, of the others. And so the problem then is how we are going to decide whether or not there are groups. We take a quantile of the set jumps, we select one. I will say a little bit about alpha 1, the quantile selected in a moment. And then we have to make a test with the reference distribution that we have generated of the values of the quantile. And then we have to decide the type of error, the alpha. There is another alpha 2, the alpha 2 that we are going to use for the test. And then if the quantile is larger than the value, the reference value in the distribution, that the quantile depends on alpha 1 and the reference distribution of this alpha 2, and then we reject the hypothesis that the data is homogeneous, and we split the sample. And that's what we are going to do all the time. So how to choose alpha 1 and alpha 2? Well, that's complicated because it depends on the sample size, on the number of groups, on the dynamic of the series. And we have made many simulations and found a simple way to do so. And the solution is we take alpha 1 equal alpha 2. There is always one alpha, a small alpha, a value. So we are going to use always one of the largest quantile, the largest quantile that maybe could be the maximum. I mean, if you have a small data set, could be the maximum. If not, would be one of the largest one. And then we employ three test statistics: 0.01, 0.025, and 0.05. And then if we reject in the process with any of these quantile, then we assume that there are groups. Note, at first sight, it could be, well, that it doesn't make any sense, because if we reject with 0.01, of course you will reject with 0.05. But take into account that we are using in different part and in different groups, not in the same group. In the same group, it would be like this. But sometimes it will be rejected with a value in one group and with another value in another. So if it is rejected with any of these values in one of the groups, we assume that we have to split the sample. And that's the main idea. Okay, and so we start. So here is summary. We start with two clusters and test the null hypothesis that each cluster is indeed homogeneous. If the null hypothesis of single cluster is rejected, then we split and we do it again. And we do so until the end. It's very easy to show that the procedure is consistent. Why? Because the distance, we assume, of course, if we are using a distance that is consistent. Why? Because suppose that we are using the autocorrelation coefficient. The autocorrelation coefficient converges, under very general condition, to the true coefficients. That means that if we have series generated with different autocorrelation structure, when the sample goes to infinity, then the sample autocorrelation will go to the true autocorrelation, and so the distance between observation in the same group will go to 0, all of them, and whereas distance between different groups will go to some positive value. So the procedure will be consistent. And also the procedure is obviously coherent because it has been built to be so in this way. So all the groups are tested with the same idea. And not all, as far as we know, no other procedure that have been proposed have this problem. And we compare the proposed method for selecting the number of clusters with the silhouette and gap statistics that are one of the tests that has been used more often. Well, I will summarize very briefly the simulation. So we consider here a small, so there are, I'm going to show two simulations, one for a small sample and another for large sample. For a small sample, so you see that the cluster size here you have always less than 50 time series, a small number of time series. So for the first simulation, we have a single group. In the second, we have two groups. The details of the groups are in the previous transparency, but I'm going to skip the different autoregressive processes or moving average and so on. Then three groups. We have generated three groups with a T distribution in which the estimation of the autocorrelation coefficient is not so efficient, and so the procedure are expected to work worse, and to see the behavior of all of them. And then four groups. You see the groups, and in all these cases we have normal noise, and so the estimation is efficient and goes fast. The estimation of the autocorrelation coefficients, and here we have used autocorrelation coefficient as distance, and you see that for testing the hypothesis that there are groups, the silhouette statistic has no way to do so. They all this criteria always assume that you have groups, so there are no testing. Cannot be done. Yes, it can be done with gap, and the jump is better. Silhouette works very well for two groups, as you see, and for three groups, gap is the winner, and with 5 groups larger, our test is much better. As you see, the other really doesn't work when the number of groups grows. And if you increase the sample size, a similar situation happens. So the test always is the best for testing no groups. For 2 groups, silhouette works always very well, surprisingly. For 3, gap is the winner, although the differences now are smaller. But for 5 groups, well, 5 groups and sample size 300, none of them really is very effective, although a jump is the best one. But if we increase the sample size and take 500 time series, I'm sorry, no, and the sample size, the period of observation T, also we increase the cluster size as well, the jump statistics works better. So the criteria seems to work well, although no, it's not better in all situations than the other one in the finite sense simulation that we have shown, but overall it seems to work better than the others, and of course it has better theoretical properties. So I have an example, but I think I'm going to skip the example. Well, we have very briefly, where I will say 2 words about the sample. We have series of the European area. We have GDP, consumption and investment of different countries. We have 75 a period of T 75 time points and 57 time series. And we apply the silhouette, the gap, and our criteria, and the silhouette and gap statistics select 2 clusters, and our criteria specifies 3. This is the dendrogram, and if you look at the dendrogram, 2 groups are quite sensible because you have the symmetry, but it could be 3. Maybe we can cut a little bit over here and find 3, or even 4. And we have here is a justification of the cluster that we found. All of them, so this is a common cluster with silhouette and gap, but our cluster note is important note that the scale in each plot is different. Okay, that means that here there is a large variability, this is smaller variability, and this is very small variability. And what silhouette and cluster and gap did was to put these 2 groups together, whereas in reality they are really different. The series in these 2 groups are very different. And let me try to convince you of this. You see here first, in this group, this is the split that our criteria has made. And in this group, you see that all the series have a common behavior. They have low variability before the crisis and very large variability after the crisis of 2012. From here, you see that there is a large variability. Whereas here, none of the series have a large variability. All of them, you see, is 0.1 and 0.1, 0.2 and 0.2, you see. So the variability of all the series more or less is like this. You see, very small is that one. So it makes sense. And of course, if you look at the series, at the countries involved, it makes sense. And we think that we get a better explanation of what happened with our classification. So in summary, because I think I'm running out of time, the procedure that I have presented based on the jumps allow us to decide first if there are groups in the data, and second, how many. And we decide everything always doing exactly the same. A very simple thing. That means the tool that we use is to simulate the jump distribution. And in the case of independent data, the way to generate the jump distribution is very easy, because you just take a representative series of the whole set and use this series to generate series that are similar to them, that follow the same structure, and we can generate as many sets of group of series as we want, and then we can apply to each set the procedure and generate the jump reference distribution. The procedure seems to work well and better than the silhouette and the gap statistics, that are 2 more used criteria in hierarchical clustering. And it has a good property that we like it very much, that is coherent. That means if I say this is the classification and this is a group, then you apply in the criteria and you check that effectively is a group. None the silhouette, not the gap statistic have this property. And of course, the procedure, you have a distance that is consistent, that means that group, the distance between elements of the same group goes to 0, the criteria, of course, then is consistent. Whereas most of the criteria do not have these properties. And there are, if you are interested in the quantiles, how to find a representative element, or actually I mean, all sorts of quantiles from a data set. There is a paper in Technometrics that we wrote about it. So it's similar to the idea of depth, but for time series. And you are interested in clustering by dependency, there is this paper, and also in the Journal of Econometrics, there is one applied to factor analysis. And some of these ideas are in the book that Ray and myself wrote on statistical learning with the big dependent data, in which we talk about cluster and we talk about these ideas as well. And muito obrigado pela atenção. Thank you very much.